Okay, welcome Regents students to today's topic, which is the electromagnetic spectrum or electromagnetic waves. Yesterday we learned in the sound waves unit, the sound waves topic, that sound is created when you take a physical object like your vocal cords, a reed in a musical instrument, or a guitar string, and you vibrate it, and that physical object vibrating against air molecules or any other molecules causes vibrations that travel, or longitudinal waves, which we call sound waves. And sound was, it needed matter to travel through, so because it was vibrating atoms. Today, we're not vibrating like a speaker or a guitar string. What we're going to be doing is studying what happens when you vibrate charge. A reminder, charge. Charge can be produced or accumulated by taking an object, plastic, like maybe a comb, and rubbing it through fur, or maybe my hair. So maybe I comb my hair on a dry day and the comb gets statically, electrically charged, becomes negative. And so we learned from the electrostatic unit that that negatively charged comb has an electric field that points toward it. If it were positive, it would have an electric field that points away from it. But it's negative, so it points toward the comb. And then we learned in the magnetism unit, when you move charge in an electric circuit with current, that makes magnetic field. So charge makes both electric field and magnetic when it moves. So if I wiggle this comb, I will be wiggling the electric field and the magnetic fields caused by the comb. And so that wiggling, electric and magnetic fields traveling, the vibrations traveling through space is what we call electromagnetic waves. This is a diagram that shows what's happening with the electric and magnetic fields. Probably looks very complicated. If you don't want to draw it, you don't have to, because something like this is not part of the Regents curriculum. I just like drawing my 3D diagrams and thinking about electric and magnetic fields in 3D. So that's why I drew it. And so I'll just explain what's going on, and then I'll show you an alternative if you don't want to draw that, because it's pretty complicated. So you see the electric field here. It's basically tracing out a cosine graph. You see these arrows. If you draw a line through the tips of the arrows, starts high, goes down below the axis here, goes up above the axis, and so it's cosine graph. Okay, and the magnetic field's like a cosine graph in this direction, perpendicular to the electric field vector. And if I draw a line through here, you'll see it also traces out a cosine graph. So those are the disturbances in electric and magnetic field that travel through space with a velocity. So the electric fields are vibrating this way, the magnetic fields side to side, and the velocity is that way, perpendicular to the fields, to the vibrations. That makes this a transverse wave. Unlike yesterday's sound, which was a longitudinal wave, the vibrations were like this and the wave went like this. Here we're vibrating like this, and the wave goes like that. So perpendicular transverse waves. Again, as I said, you don't have to draw that diagram. If you wanted to draw something as simple as this, it would be sufficient. Okay, so you have just E and B electromagnetic fields vibrating, and that vibration moves that way, making a transverse wave. So electromagnetic waves or radiation are vibrating electromagnetic fields. They're transverse waves that can travel through vacuum, and often, though not always, through matter. So that is different than sound. Remember, sound could not go through vacuum because there were no atoms there to vibrate. Electric and magnetic fields can vibrate with no matter present whatsoever in the vacuum of space. So electromagnetic waves can and do go through space, and I'll explain a little bit more about that later. Okay, so I can wiggle this slowly and create a small frequency, maybe 2 hertz or something. And I would be making an electromagnetic wave with a frequency of 2 hertz traveling through space. We'll talk about the speed later. And if I go faster and make a higher frequency from V equals lambda times frequency, with a bigger frequency, you get a smaller wavelength. So I make more frequency and the wavelengths get shorter and shorter the faster I shake this comb. So it's just, I can make whatever frequency I want by just shaking, charge whatever frequency I want. But let's suppose that I shake faster and faster, and I can shake this comb 880,000 times per second. Okay, I can't do that physically, but let's suppose I could, 880,000 times in 1 second. Okay. What would happen in this instance? By the way, that's 8.8 times 10 to the 5th hertz, or 880 kilohertz. Anyone in the vicinity listening to their radio, the AM station of 880 for their news or their traffic report, would suddenly hear static because I would be making a wave of 880. And their radio is tuned to receive that from a radio station. But I'm shaking the comb and suddenly I'm interfering with it, and their news program would cut out and they'd hear static of me doing this. Literally by shaking the comb at 880,000 hertz. That's what the 880 radio station is. It's an electromagnetic wave. Okay? In fact, we can see in our reference table the electromagnetic spectrum. So that's here, page 2 of the reference table. You don't obviously have to copy this down because it is already, you have it available for the Regents and all your quizzes in physics. So here you see I had that frequency of 8.8 times 10 to the 5th. If you look here along the diagram, somewhere around here, 8.8 times 10 to the 5th is between 10 to the 5th and 10 to the 6th. I am at the bottom edge of what we call the AM radio wave spectrum of the electromagnetic spectrum. If I shake faster and I go to about 1,000,000 times per second, 1,010,000 times per second, which is 10 to the 6th, you see that falls again in that AM range, which is in kilohertz, 1010, or as they say on the program, 1010 wins, 1010 AM radio. And I'm shaking a comb and I can make that. Obviously not with a comb because there's too much inertia to shake it that fast. But in theory it's possible. The way they do it at the radio station is they just have an antenna, a metal spike going way up into the sky, and they just make electrons go up and down at that frequency. And that's how they broadcast that radio station, 1010 or 880 or any FM wave station. If I shake faster still, you see that basically I am somewhere in this region. If I shake 100,300,000 times per second, which is 1 times 10 to the 8th, or 100.3 megahertz, that's Z100. Shaking this comb 100 million times a second, I am right here, I'm in the FM part of the spectrum, and I could interfere with Z100 by making my own electromagnetic wave that goes into people's car radios. So that's what these are. They're these invisible vibrations of electric and magnetic field that then when they hit the radio antenna, they cause the radio's antenna to vibrate, which the radio picks up, and then they can encode music in those vibrating electric and magnetic fields. In fact, if you look at an FM radio, you'll see Z100.3, and then if you look closely, you'll see the units of megahertz. Okay, and with AM, like 1010, if you look closely, the dial will be marked as kilohertz. Okay, so that's all that these are. There's no real difference between these two waves. It's not like if you were able to see these electric and magnetic fields, they would look any different. The only difference is that the frequency of vibration is higher and the wavelength is therefore longer. So the wavelength is between 10 to the 0 and 10 to the 1. So somewhere between 1 and 10 meters. And then for AM waves, they're like 100 to 1,000 meters long. So longer wavelength and smaller frequency is all that distinguishes these two waves. These things, these names, FM and AM, are just names that humans gave to these vibrating electric and magnetic fields. In nature, there's no difference between the different fields. It's just humans put labels on them. So back to my shaking comb, and also notice the overlap. Is it if it was a 1010 and I asked you what kind of wave is that, and you said it's a TV wave, or an FM wave, or a radio wave, all those are correct answers because different people at different times label things differently. So as long as you find one of the categories that matches the wavelength on a quiz or test and you identify that wave by any one of the categories, then that's correct. But for example, if you called it an infrared wave and it was right here, well, that's wrong, right? So anything in that region you can call the wave that. So back to my shaking comb, I shake faster and faster. And then let's suppose I go into 1.8 gigahertz. So that's, giga is 10 to the 9. So we're talking about 1.8 billion times per second. I'm shaking that comb. Those are the frequencies of your cell phone, 1.8 gigahertz, which is 1.8 gigahertz, 10 to the 9th. It's right here somewhere is the frequencies of your cell phones. So that is a microwave. If I shake instead of 1.8 to 2.4 gigahertz, so just a little bit higher frequency, I get into the microwaves that are in the ovens when you cook your food. So that's an interesting thing that people worry about. Okay, my cell phone next to my brain is 1.8 gigahertz. I put my chicken into the microwave oven at 2.4 gigahertz and it cooks the chicken. Am I cooking my brain? Well, there's people that will argue both ways and say, some will say, no, you're not, it's perfectly safe. Others say, geez, your brain is getting irradiated to a dangerous level. So that's, I'm not going to talk about that here because I'm going to steer clear of controversies. But that's cell phones and microwave ovens are somewhere in this region. I shake faster and faster, and then I get out of the microwaves and I get to the infrared. You wouldn't see that, but basically what would happen is infrared is like heat. So I go like this, I'm shaking the comb, let's say 10 to the 13th times per second. So I 1 with 13 zeros, that many times per second. That's how fast I'm shaking the comb. And I hold my hand right here, and I'm shaking, and I feel my hand nice and warm, like heat lamps that you might put for, maybe you have a pet or something, a snake, and you put the infrared light on to keep it warm, okay? I shake faster and faster, and then something pretty interesting, amazing starts to happen. If I can shake faster than 3.8 times 10 to the 14th, that's right here. See this little section right here? It's blown up down here. So I'm shaking at 3.8 times 10 to the 14th hertz, or a little bit beyond, maybe 3.9. You wouldn't see a comb because I'm shaking it so fast it'd be a blur. But coming from this region, it looked like there was a red lamp over here. Glowing. Red light would be going all through the room and lighting up the walls. They'd be glowing red because I'm shaking a comb. That's all that red light is. It's vibrating electric and magnetic fields between 3.8 and 4.8 times 10 to the 14th hertz. Why those? Well, that's when you look at this paper and you see red. That light, those fields are vibrating like that. They go into your eye and your brain looks, and everyone says this is red unless you're colorblind. So we could all say that's red. So we can measure those frequencies. We see anything between here, humans will call red. Maybe a slightly darker red, a slightly lighter red, but all different shades of red. And I shake the comb faster, and I go beyond 4.8 to maybe 5 times 10 to the 14th between these two numbers, and then you'd see an orange glow coming from this shaking comb. Shake faster, yellow glow, green glow, blue glow, violet. So I go through the whole rainbow by just shaking the comb faster, and I'm making light out of a shaking charge, which shakes electric and magnetic field. Then eventually I shake faster, and we go beyond 7.69 times 10 to the 14th. beyond violet light into ultraviolet. And our eyes can no longer detect that. Remember yesterday I said our ears can only hear between 20 and 20,000 hertz. And you should have experienced that when you played around with that tone generator. Same thing, human eyes, these ultraviolet waves can go into the eye and the eye doesn't see them. It doesn't detect them. So I could be making ultraviolet rays and turn off all the lights and you're looking, you say, oh, it's dark, there are no waves. No, there are waves that are going in your eyes that your eye nerves don't respond to. So we don't see them. And so ultraviolet, I'm shaking like this and you hold your hand, you can't see anything, but maybe you get a tan. UV light makes tan. That's what we have in tanning beds. I shake faster still, I can make x-rays, and then maybe I'm shaking this like this and I put a film back here and then the x-rays are going through and then we could see my bones from the x-rays. So they're just vibrating electric and magnetic fields that can pass through flesh but not through bones. And so we can see images of bones with the x-rays. And I shake the fastest, from 10 to the 19th or 10 to the 18th, somewhere around there beyond, and we get to gamma rays, the most energetic, most dangerous. These are produced a lot of times in nuclear reactions that can cause radiation damage to people. So that's the electromagnetic spectrum. All just vibrating electric and magnetic fields of different frequencies and different wavelengths. Some of them we can see with our naked eye. They're visible, so we say they're visible light. But they're no different scientifically from radio waves, microwaves, or ultraviolet. They work the same way, vibrating electric and magnetic fields. All right, so that's obviously available to you on tests and the Regents. Let's go on. So we got the electromagnetic spectrum, page 2 of the reference table. And then the speed of electromagnetic waves. All of these waves travel at the same speed through space. Okay, but it's not called, the reason why I crossed it out is it is not called the speed of electromagnetic waves. On the reference table, the speed of all these waves is listed as the speed of light. That's done for historical reasons. Albert Einstein basically based a lot of his theories on the speed of light. So we call it the speed of light, v, and we give it its own symbol because it comes into play in so many physics theories, okay, about time and space. It gets its own special symbol. And so we call it c instead of v, 3 times 10 to the 8th meters second. And so here we have, where is the speed of light? Again, front cover of the reference table. Not the speed of electromagnetic waves, but the speed of light. You have to realize this is X-rays, gamma rays, infrared, ultraviolet. All of them have this speed of c, 3 times 10 to the 8th meters per second. Okay, front cover of the reference table. Okay, so then once again in the waves topic, the two kinds of calculations we can do is with D equals VIT, no 1/2 AT squared. So this is from mechanics, this formula. And in fact, you don't even need the VI there. You could just put D equals V times T, or V equals lambda times frequency. So let's look at a couple calculation examples. So here's one. How long does it take for light from the sun to reach the earth? Okay, so we use D equals VIT. This is from the reference table, the distance from the sun to the earth, front cover, mean distance, earth to sun, right here, okay, 1.5 times 10 to the 11th. So I take that, I put it in there, and then the speed of the wave, again, I get from the reference table, speed of light, 3 times 10 to the 8th. And so I solve and I get 500 seconds, which is about 8.3 minutes. So that's how long it takes light to go from the sun to reach the earth. So let's suppose in theory we have a superhero villain and they steal the sun. For 8 minutes we would be standing here looking at the sunlight saying, oh, what a beautiful sun. Because that light ceased to come from the sun, but the light that just emitted is going to take 8 minutes to get to the earth. So there'd be a delay before we'd notice that the sun went out of 8 minutes. Okay, because that's how long. And again, the light goes through vacuum of space, but not the sound of the sun. We don't hear it. Okay, second example. An electromagnetic wave has a wavelength of 5.25 times 10 to the minus 7 meters. Determine its frequency, and B, identify the wave. So we just use V equals lambda times frequency, front cover 3 times 10 to the 8th. We plug in the wavelength, we solve for the frequency, 5.71 times 10 to the 14th hertz. And then, what kind of identify the wave? What we do is we go to the reference table and we see, first of all, 10 to the 14th. So we find that 10 to the 14th, okay, it's between here and here. 10 to the 14th here, 10 to the 15th. Maybe it's visible light. So we look now at the number, 5.71. Between 3.8 and 7.69, 10 to the 14th, is visible light. 5.71 is between here and there. So that, if you look, is what humans would label as green light. So that's what we'd label. That'd be the answer to that question. The last thing, polarizers. Okay, so I forgot my 3D glasses downstairs. I have some 3D glasses. I totally forgot that I need them for the video. But basically, polarized, you've probably heard this. A lot of glasses are polarized. A polarizer are transparent materials with tiny invisible grooves that block light not aligned with the grooves. So you have unpolarized light. The electric fields, for example, could vibrate in any direction, up, down, side to side, as the light is moving sideways, transverse waves, so random vibrations, okay? And then, if it encounters a piece of glass with these grooves in it going up and down, any side-to-side vibration gets blocked by the grooves, and only up and down vibrations can pass through those slits. And so that is now polarized light. All the electric fields are vibrating in one direction. Okay? If you put a second polarizer going sideways, notice these grooves go up and down, this goes sideways, then these up and down vibrations, the polarized light cannot get through that polarizer, and so no light goes through. You look through one polarizer, you could see through it. You look through the other polarizer, you can see through that one also. You put them together, 90 degrees to each other, and it blocks light. So no light gets through. This is used in sunglasses because light that reflects off of surfaces tends to be polarized. So imagine a wet road and you're driving and the sun hits it and it glares and shines in your eye, and now you can't see the obstacles, the pedestrians, the cars, or whatever, because your eyes are getting blinded by the glare. So you put a polarizer and you arrange it in the glasses, the manufacturer does, so that it's always perpendicular to the way that surfaces, the light gets polarized when it reflects off a horizontal surface, and it blocks that reflected light so the glare is gone and you're not blinded anymore. So that's how those work. 3D glasses, as I mentioned, they have two polarizers, one for one eye like this and one for one eye like that. And so your left eye sees light that's only polarized side to side, and your right eye up and down. And so what they can do is on the same screen they could project two movies, one whole movie for what your left eye should see by making that polarized this way, and then another whole movie that's this way for your right eye polarized. And so by seeing two different views of the same movie, it's like what you see when you have your two eyes separated to the side by a certain distance, and you look at the whole world with your left eye, you look at your whole world with the right eye, and you see two slightly different images, and that gives you the perception of a 3D world on a flat screen. Okay, so that's polarized. I'm going to come back and make a quick short video with the polarized glasses because I think that will be interesting for you to see how the polarizers work. Okay, see you in a bit.